what we're going to look at today is going to be finding the area of what's called a regular polygon. We dealt with regular polygons back in first semester when we talked about exterior angles, interior angles, side lengths, and stuff like that. We've worked with them before, but what we're going to do a little bit differently today is we're going to add, I don't know, probably 2 steps to what the stuff we have done in the past. Do you guys remember what a regular polygon was defined as? Closed figure, all sides are, then what makes it regular? Until it gets to an angle. Oh yeah, I know. Just being. Because do you know what this is when you start doing stuff like this? That's polar coordinates. That's stuff you do late second semester of pre-calc if you really want to get crazy. You can actually graph stuff like that with trig functions, but that's so regular polygons were polygons with all sides congruent and all angles congruent. It's your stop sign. It's a pentagon. It's a square. It's an equilateral triangle. Things like that. What? A dodecagon. Okay. Well, what is a decagon? What's deca? Deca. Decade.
How many years in a decade?
At least he's honest. You know, he's like, I don't. So remember, a lot of times when we did this. What was that? Fifth grade. Chapter 5. I don't know. It was towards the end of the semester, I believe. Yeah. So we had 5 sides were a pentagon. 6 was the hexagon. 7 was the heptagon. Or a septagon, however depends on where and when you grew up. Really.
I like the septagon because then it goes in line with the octagon, decagon, in terms of September, October, November, December.
Or SE for 7. I don't know. It's a nickname. The septagon was hanging out for so long, people kind of thought he was cool, so he was hip, so they called him a heptagon.
Don't ask him that. Remember the story he told about the Romans or something? How he started trade? I was like, what is he talking about? This is trying.
There's a class in college where you can get an MA, an MS, a BA, or a BS. Yeah, I got a degree in BS.
You got a degree in all that?
Technically, it is. It's a BS in math.
Also called a decagon. Like uno is 1 and deca is 10.
I just made up the ones I got. Sorry. No, those are all the ones that you guys have to know the names of because they say, hey, here's a decagon. You'll have to know, oh, that's 10 sides. Everything else will be called a 11-gon, 13-gon, 77-gon, and so on and so on and so on. 3-sided figures are obviously going to be equilateral triangles. 4-sided figures will obviously then be squares because those are the regular polygons of that. So everything else is just called what we say an n-gon, and n is just the number of sides. All right, and I know that this is review. You guys have all seen this, and it's not going to be so that vaguely ring a bell? Now, one of the things that we did when we dealt with regular polygons is that remember how I always said don't draw the figure, because Lord knows drawing these figures is not that nice and they don't look all that great. But no matter what, in each of these figures, there's always going to be at least 3 sides connected. Are we okay with that idea? So we drew this all the time. We drew this same thing over and over again. Remember that? Now, when we did that, we always worked by finding that exterior angle here. Remember that? So, in order for us to figure out what that exterior angle was, we used what we called the sum of the exterior. No matter what shape you have, how many degrees does it always take you to get around an object? 360. Now, with these being what are called regular polygons, that means that every single one of the inside angles and every single one of the outside angles are always going to be, all the inside angles are the same, all the outside angles are the same. So in order to figure out what the outside angle is, we always did this. We took 360 divided by the number of sides, and this equaled your exterior angle. You okay with that? And we used that a lot last semester. What's going to be different with it this semester is that we're not only going to be working with the outside angle, but we're going to take a couple steps to work with the inside angles. For example, let's say we have a pentagon. All right, let's say we have a pentagon. And if we have a pentagon, how many sides is that? 5, good. So that means that I would take 360 and divide that by 5, and I would get my outside angle. So what's 360 divided by 5? Very good. It's 72. Okay. So that means my outside angle is 72. So if my outside angle is 72, what's my inside angle? 108. Very good, because they're always going to be what? Excellent. They're supplementary. Outside angles and inside angles always add up to equal 180 because they're supplementary. So that gets you inside the pentagon, and every one of these is going to have an interior angle of 180. Will that change for any pentagon? Nope. Just like every time I see a pentagon, I know I have an outside angle of 72, inside angle of 108, and that will never ever change. And after we go through a few of these things, we're only going to see so many shapes, which means we're only going to see so many angles. And it happens to be kind of repetitive after a while. Now, there's these couple of new parts that we're going to add into our shapes here. And I know I said that we don't have to really worry about drawing the full thing, but what I wanted to do real quick is just take a pentagon real fast and explain to you other parts that are in these regular polygons. Yes, sir?
So that was like a 360.
There's 360 sides? Yeah. Yep. Each angle on the outside would be 1, and then the interior angle then would be 179. The more sides you have, the more of a curved shape it looks, but you still have, no matter what, you're still going to have 3 sides that connect. So all these distances aren't going to be the same from the center point. That doesn't happen until it becomes perfect. So what happens here is we take a pentagon, or any regular polygon, if you will. You guys ever heard of the term inscribed? What does inscribed mean? Inscribed means that I place a figure inside of a circle. I place this figure inside the circle so that all the vertices touch the circle. You okay with that? That's what it means by inscribing. So if I have the center of a circle and it goes from the center to the side, what is that called? When I go from the center of a circle and I draw to the side where it touches the circle, what's that called? Radius. Okay. So in every regular polygon, we can draw radii to each and every vertex. And all those radii are always going to be the same. You okay with that? Yes, no, maybe so. Now, what happens with these things being what we call regular is that the radius always, always, always bisects the angles, no matter what. No matter what regular polygon you have, that radius will always bisect that angle. So that creates these parts all being the same going all the way around. Now, in a minute ago, we said that we were putting a pentagon in there. You told me that the outside angle was 72, the inside angle is 108. If I cut the 108s in half, what do we get? How much? 54. I thought you said 3 for a second there. That gives me 54 here and 54 here. Be okay with that? Now, here's what we're going to do. What we do with regular polygons is we're going to draw in this new piece. This new piece goes from the center to the side, and it is the perpendicular bisector of that. That part is called an apothem. Apothem or apothegm, some people call it. You say apothegm or apothem?
I say apothem because apothegm sounds like a possum.
My parents had it. You guys ever seen a Shiba Inu? It's like a small Akita dog, right? They're terribly loyal and they're vicious. If something comes up to them, they're bred as hunting dogs in Japan. So they see small creatures and they just want to kill them. But then they're vulnerable. So they love being outside because they're thick coats of fur and all that stuff. So my parents had it. They had this little dog hut, like a little igloo. His name was Sammy. So Sammy would go outside all the time, and they lived kind of like a little foresty area. So there was always creatures walking by, and Sammy would kill, I think, 2 or 3 different possums in his time. They would sneak up, try to take his food, and he would just kill Sammy. You know how like the Red Baron from Snoopy had little tick marks on the side of his airplane? So we started putting possum stickers on his igloo. Anyway, so look at talking. We get this thing called an apothem. So what we're going to do here is every time we draw this 3-sided figure, we're going to put in an imaginary center, draw an apothem, and do that. Because then we can draw a radius and bisect our angle, and we create a right triangle. Which means we're going to be able to find areas of regular polygons by doing a little bit of work. And each one of these problems are going to be basically the same generic setup. The formula for finding the area of a regular polygon is this. The area of every single regular polygon is going to be 1/2 the perimeter of the polygon times the apothem, which is we use a lowercase a. And I'll show you an example. We'll use the pentagon, and we'll get a side length, and we'll walk through it. And it is, you will have to use a little bit of trig sometimes, but we're talking sine, cosine, tangent, because you have a right triangle. You might have 30, 60, 90s, so you can use special right triangles if you'd like. Sometimes, depending upon the information you have, you might just have to use Pythagorean theorem. Okay? It all depends on what you know. But that little generic drawing of that 3-sided figure with that vertical coming down that bisects is the same thing we're going to use over and over and over and over. Okay? So back to our pentagon. Let's say we have a pentagon, a regular pentagon with side lengths equal to 8. We'll make a nice easy number to work with. Which means we have our 3-sided figure, center point, drop down, bisect, bisect, radius, exterior angle. That's basically what you're going to draw every single time for every problem, because no matter what, it's always the same. Yes, ma'am. Yes, ma'am. Because I don't want you to draw the shape. I just want you to draw the 3 sides. It's easier. You have to trust me on this one. It's less work and less stuff you have to look at. Yeah, and that's the other thing. Once you know, if you remember that pentagons are always 108, that never changes either. So here's what we do. We know that we have sides of 8. So what I do is, after I draw my 3-sided figure with all the parts, I know this is an 8. The 8 gets bisected, which makes both those pieces how much? 4s. So I did my sides. we know that that exterior angle, because we did it a minute ago, we took 360, we divided by 5, and we got 72. That gave us our outside angle. That gives us an inside angle of 108. Oops. An inside angle of 108. And if you cut that in half, what do you get? 54. What we need to find out now is, what's this apothem? We don't know this length. But if you look inside that triangle, you have an angle. You're trying to figure out its opposite, and you know it's adjacent. What trig function is opposite adjacent? Tangent. Which means that the tangent of 54 is my apothem over 4. And I'm only using the 4 part because the 4 is just the piece that's connected there to make the right triangle. I'm not using that entire 8 bit. I'm just using that 4. Okay? Which means when I have to solve for my unknown that's in the numerator, what do I have to do with the denominator? What's that? Put a 1 where? How do I move that 4? Multiply it over. So I get this value of 4 times the tangent of 54 is my apothem. Or use my calculator. I have one out. Would you say that's 550? And always round these 2 decimals, because this is the thing you'll have to start rounding a little bit here and there. And depending upon the angles, you might get √3s, you might get √2s, you might get halvesies, you never know. It really depends upon the problem. So we had 4 tangent 54, like Josh just said, is 5.51. That's my apple. So we know that the formula is going to be 1/2 the perimeter times the apothem. Well, how many sides does a pentagon have? And each of those sides is equal to? So what's your perimeter? 40. So you know that your perimeter, since you have sides of 8, your perimeter is going to equal 5 times 8, which is 40. So your answer is 1/2 40 times 5.51. And that gives you your area of the regular column. There's many steps to this, but it's the same process over and over and over and over again. Once we do a few of these, it never changes. Okay. Josh, when you press those buttons, what'd you get? 110.2. Anybody else all right with that? I multiplied 1/2 times 40 times 5.51. Easy way to do that in the calculator is just go 0.5 times 40 times 5.51. 110.2. Like the man said. Something square. Okay. There's 5 side lengths of 8. Every problem is very, very, very similar to this. Sometimes they'll give you the apothem, sometimes they don't. Sometimes you got to find the apothem, sometimes you got to find a side. Let's try another one. Let's say we have a hexagon. Say we have a hexagon with side lengths of 10. So if we have a hexagon, side lengths of 10, how many sides is a hexagon? 6. So if I have sides of 10, that means right off the bat, I know my perimeter is going to be 6 times 10, which is 60. That's easy enough to figure out. Now, draw the figure. It's going to be the exact same figure every time. 3 sides. Apothem, perpendicular bisector, radius, exterior angle. Very good. Just like we've done before, to get that exterior angle, we take 360 divided by the number of sides. You get 60. If your outside angle is 60, the inside angle is something, 120, very good. Half of it then is 60. You okay with that? What's half of 120? Remember that radius piece that goes to the vertex always bisects that angle. Okay, that always does. Your side lengths, you know that the whole side length was 10. Each of these two parts then will be how much? 5. Good. And now you're back to a right triangle. You have a 5, and you're trying to figure out what your apothem is. There's one of two ways you can do this. It's a third, very good. It's a 30, 60, 90 if you pick up on that. Or if you want to use trig to solve for it, use trig to solve for it. Either way, you're going to get the exact same answer. If I use trig, I have a 60, and I'm trying to find the opposite, and I know my adjacent. What function is that again? Tangent. If I use 30, 60, 90, I know that I'm opposite my 30 is 5, which means opposite my 60 would be 5√3, or like you said, if you want to use trig, you get the same thing. Press a bunch of buttons and your calculator will spit out 5√3. Okay. There's your apothem. We've already figured out the perimeter, so what do? Exactly. Let's write it out loud. 1/2 perimeter apothem. Yes, sir. Yep. If the calculator gives you 5√3, if you just keep it like that, if you type it in, I think if you type this one in like that, you go 0.5 times 60 times 5√3. Does it give you in √3? Oh, okay. I bet you it'll give you the √3 if you did 1/2. Because depending on how you write it, oh, okay. Thank you. I didn't realize that. I'm like, wait, that's not. Because say, how did I not get the same answer twice? Yeah, thanks. I didn't notice that. So yeah, the depends how you type it in. More often than not, I mean, if I'm looking at that and I know it's 30 times 5, I might have written 150 √3. That would have been an exact answer. Or decimal, you get 259.81. Yes, sir. Oh, because you know why? Because you rounded at first. Okay. And that's fine, Josh, because what you did was you wrote down that this answer, you simplified that first, and then as long as you write down what you used again here, that's fine. By not simplifying here, this answer is technically more correct, albeit, we're talking 7 thousandths versus what you have with your rounding. It's just the longer you wait to round something, the more accurate your answer is. You're not wrong. It's just less right. Josh, as long as you wrote down what you did, I'm not going to mark anything off. And plus, you're within point something. It's close enough. Okay. Like I said, it seems like there's a lot going on here, but in all honesty, it's kind of the same problem over and over again. Yeah. Let's try a different one. Let's say we have an octagon that has an apothem of 5. And we'll make something up. Oh, man, that's weird. It's only like, what, 4th time this whole year dropped that. So, octagon, apothem of 5. What do you want to start with? What should you start drawing? 3 sides, yeah. Draw your 3 sides. center, perpendicular bisector, exterior angle, and a radius. In this case, I know apothem is 5. What do I do then to figure out my exterior angle? Well, how many sides does an eye have? 8. My exterior angle is going to be 360 divided by, which gives you 45. Very good. You have 45 degrees, and then your supplement of 45 degrees would be 135. Very good. So that whole inside angle will be 135, which makes the small angle half of that. Yes, ma'am. Yes, ma'am. Yeah. Because you first, remember that 45-degree angle gets you the outside. The 135 is the inside. The radius cuts that in half. So your inside angle is 67.5, and you need to figure out that section. What trig function are you going to use? Have you sensed the pattern? More often than not, you're going to use tangent because it's very rare that you're going to have the angle at the apothem because that's a lot harder to find. You can find it, it just sucks, to be honest with you. It's not easy to work with. That's why I always work outside in. Remember we said this before, it's always easier to work with your outside angles to get inside the polygons because it's quicker. So if I use tangent again, I have tangent of 67.5 is our apothem over our unknown. What do you have to do when your unknown's in the denominator? Exchange-o, change-o. Press a few buttons here. 5 divided by the tangent of 67.5. And I'm getting 207. We okay with that? So that means that this portion here is 2.07, which means this portion is 2.07, which means the whole thing is 4.14. Now that's the side length then is 4.14. How many of those sides do you have? 8 of them. So that means your perimeter be 8 times the 4.14. What was it Josh said? 3312. Thank you, sir. Do you have enough information to put it all together? And this is the thing with this stuff, guys. Outside in with the angles, trig to figure out you can either miss a section or an apothem. And it's kind of the same problem over and over again. 1/2 33.12 times 5. $82.8. Something squared. And that's the stuff that we're doing today, guys. We're just piecemealing this together to start. Think you do a couple of those without too much of a hassle? All we're doing is just looking at a picture and working our way out. All right, all we're doing is looking at a picture and working our way out. Let's see. Yeah, I'm just giving you 3 to start with. I don't want to go too crazy. So that's it. That's all I want. That's all. We'll work our way into more of this stuff tomorrow. But that's based on what you learn about right now. Then you have a hexagon. I'm sorry, you actually have 2 hexagons. That's triangle. Okay. When you have a triangle, trick here. When you have the triangle, what's your outside angle? Well, we know with the triangle, it's got to be equilateral because it's all the insides are going to be 60. And if you know this side length here, when you draw this in, it's really quick to make this work. Really, really quick. And the other two are hexagons. I mean, you can probably do this with your eyes closed. An example of one in class. Cannot stress the drawing of it to make it work. We'll do more of these again tomorrow. We might even do a little bit more on Thursday before we get to the trick areas. That's kind of where we're at. Then we can do a couple of the similar figures.